Hello everybody, this is Marika Lamoureux and I am going to walk you through the steps of hand calculating a one-way between subjects ANOVA. So I know that sometimes when you are faced with a task like this, it can feel overwhelming, and this video may capture what it feels like to try and calculate a one-way between subjects ANOVA by hand. Okay, so if that video sort of captures how you feel, I hope that this demonstration will make you feel much better and make you feel like you are not literally at the end of the rope calling for help, and that you have all the resources you need to be able to do this. So let us begin. Here is the sample problem that we are going to use, and I will go ahead and read it to you. The management at a Porsche dealership wants to find out whether to keep an equal number of red, blue, and black Porsches on the lot. Here are the records of how many red, black, and blue Porsches were purchased in the last 6 months. Were an equal number of red, blue, and black Porsches purchased? And if you look at the data, you can see, for example, that only one person bought a blue Porsche in February, and in April, 11 people bought black Porsches. So here's the data, and before we start actually calculating anything, we need to think about what the null and alternative hypotheses are. So if you remember, for a t-test, in a t-test you say that the null hypothesis is that there's no difference between your two samples. And in an ANOVA, you have more than 2 levels that you're testing. And in this example, we have 3 levels. We have red, blue, and black. So if we were doing a t-test, we would say there was no difference between our 2 levels. And with an ANOVA, we're going to say there's no difference between our 3 levels. And it looks like this. There's no difference in how many people purchased red, blue, and black cars. And when that's kind of expressed in a mathematical way, then that reads H naught, states that the mean of the red group is equal to the mean of the blue group, which is equal to the mean of the black group. And if we are looking at the alternative hypothesis, the alternative is that there is a difference in how many people purchased red, blue, and black cars. And that's what it looks like stated in a mathematical version. So now we are going to look at the list of formulas. And I know that this is a lot of formulas, and that some of you may be pulling your hair out thinking, oh my goodness, how am I ever going to be able to use all these formulas? It's very intimidating and scary. Well, first of all, formulas are our friends, and we like formulas. And these formulas are going to help us and walk us through step by step everything that we need to know. And I will talk you through the entire process. So if you want to calculate an ANOVA, what you're trying to actually calculate is an F value. And if you look down at the bottom middle of the screen, you can see the formula for F. And the formula for F is mean square between over mean square within. Now, how do you calculate mean square, you ask? Well, fortunately, we have a formula for that, and it's over to the left bottom. And it's that mean square equals the sum of squares over degrees of freedom. So for example, if you wanted to calculate your mean square between, it would be the sum of squares between over degrees of freedom between. How do you know what the sum of squares between is, you ask? Well, you look at the formula for sum of squares between, which is higher up on this list of formulas, and you can see that we have formulas for sum of squares within and between, and also for degrees of freedom within and between. So let's dive right in and start calculating things, and let's calculate the sum of squares within. And you can see here the data is already up And I have gone ahead and put up the sum of squares values for each level of the data. And I'm going to assume that you can calculate sum of squares for each column of data. If you can't, there are resources to help you learn how to do that. You can go to your textbook or you can look at other videos. But for the purposes of this video, I'm going to assume that you can do that. So if you look at the formula for sum of squares within, you can see that it has the spotty looking E sign, which is a sigma. And the sigma just means that you are going to be summing across all of the things that are within the sigma sign. So you're going to be summing across the sum of squares for each level. I know that's a lot of summing, but it's okay. It's just addition, and addition never hurt anybody. So what that looks like for our data set is the sum of squares within equals the sum of squares for red cars plus the sum of squares for blue cars plus the sum of squares for black cars. And we already know what those sum of squares are, so for our data set, that means the sum of squares within equals 20.83 plus 6.83 plus 15.33, which equals 43. And with that, we have already calculated one of the values that we're going to need to know to calculate f. And that's very exciting because we were thinking maybe that we couldn't do this, and now we know it's just numbers, numbers don't bite, and it's going to be a-okay. Let's go back and look at the list of formulas, and you can see that we've calculated sum of squares within, and now we're going to go ahead and calculate the sum of squares between. So the sum of squares between equals sigma, sum, of t squared over n minus g squared over n. And I know that you don't know what t and g stand for, and I am going to explain it to you. So t is the total of all the scores for each level, and g is the total of all the scores in your entire data set. So the way that looks for this data set is the sum of squares between equals the total of all the scores for the red cars squared over the n for the red cars plus the total of all the scores for the blue cars squared over the number of scores of blue cars, and the total of all of the scores for the black cars over the n for black cars minus the total of all the scores in the data set over the number of all the scores in the data set. And I know that that might still not make sense, so let's break that down even further. So the total for all of the red cars is just going to be the sum of all the values for the red cars. So 4, 6, 7, 6, 8, and 10 are just the values that we have for all of the number of cars that were bought in each of those months that were red. And you can see that the total for blue is the same thing. We're just changing the numbers to reflect the scores that we have for all the blue cars that were bought. And the total for black is the same thing. So again, this is just numbers. Numbers don't bite, and it's all okay. So we know our t values, so I'm going to go ahead and fill in this table so everything is all nice and neat, because I think that it's much easier to calculate things when things are nice and neat. So we have a table that sort of is summarizing what we're doing. And now the only other thing that we need to know to calculate sum of squares between is our grand total. And since we've already calculated our totals for each of the 3 columns, the easiest way to calculate your grand total is to just total the totals. So what that looks like is you're taking the sum of the 3 t-scores that you've just calculated to get to your g. So now we have all of the numbers that we need to calculate sum of squares between. And you can see here that all we're doing is taking our t's and our g's and our n's and putting them into this formula. And we come out with 141.44. So now we've calculated our sum of squares within and our sum of squares between. And I will tell you that we are over the biggest hump of calculations now. So already, we haven't taken that much time, and we've already gotten through the biggest hump of calculations, so you should feel very good about where you're at right now. So if you look at the formula list, you can see that there's this other formula for sum of squares, total. And when you look down at the formula for f, you can see you don't need to know the sum of squares total for f, although you do need to know it for eta squared. But I really like calculating sum of squares total because it's a really great way for me to figure out if I have made any errors. And it's because the value for sum of squares total should equal that formula, but it should also equal the sum of your sum of squares for within and sum of squares for between. So if you calculate your sum of squares total and you have the ability to compare whether your sum of squares within plus sum of squares between equals your sum of squares total, and that will tell you whether or not you've made a math error. And so I really like it because it's a really simple way to test my math. So let's go ahead and calculate sum of squares total. So we know our sum of squares within and our sum of squares between. Our sum of squares total is the sum of all of the scores squared minus our total for all of the scores over the total number of scores. So what that looks like is all this. Again, it's allowed numbers, but numbers don't bite, so it's okay. So you can see that we're just squaring each value that we have in the data set, and we're subtracting out the grand total over the total number of scores. And that gives us a value of 184.44. And we can see that if we sum together our sum of squares within and our sum of squares between, we come up with the same value of 184.44. So this is really great because now we know that we haven't made any math errors, and that's a huge relief. I know that I always worry about making math errors, and I really like being able to just calculate my sum of squares total and know for sure that there are no math errors. So that's lovely, and we can all pat ourselves on the back knowing that we haven't made any mistakes. So now we go back to our formula sheet because we've calculated our sum of squares within, we've calculated our sum of squares between, and we are ready to start calculating our mean squares. Okay, so we know our sum of squares within and our sum of squares between, and now we are going to figure out our degrees of freedom within and between. Now you should know what N stands for. N stands for the total number of scores in the sample. K stands for the total number of levels in the sample. And in this example, we have 3 levels: red, blue, and black. So our degrees of freedom within is going to be 18 minus 3, which equals 15. And our degrees of freedom between is going to be 3 minus 1, which equals 2. And now that we know our sum of squares and our degrees of freedom for both within and between, we can calculate mean square. The formula for mean square is the same for both mean square between and mean square within, and it is mean square equals the sum of square over degrees of freedom. So for mean square between, that means for the sample it equals 141.44 over 2, which equals 70.72, and our mean square within for this sample is 43 over 15, which equals 2.87. And now that we know our mean square between and our mean square within, we can finally, hallelujah, calculate f. And our value for f is going to be 70.72 over 2.87, which equals 24.64. And the very last thing that we are going to calculate is our effect size, which is eta squared. And the value for eta squared for this sample is 144.44 over 184.44, which equals 0.77. So now we can do a happy dance, maybe throw in some jazz hands, because we have calculated everything that we need to calculate for this sample. And the only thing left that we need to do is figure out whether or not we have a significant value for f. And to do that, we're going to look at the f table. This is the F table from the back of the textbook, and I am going to go out on a limb and say that probably none of you have looked at the F table before, so I'm going to talk you through it a bit first. So if you see the graph looks very similar to what we're looking at for when we look at t values. So we are looking to see if our calculated value of f falls in the critical region, in that little gray area. And if it falls in the critical region, that means you have a significant value for f. And if it falls outside of the critical region, that means you don't have a significant value for f. So in order to find a significant value, it means that our calculated value of f needs to be larger than our critical value of f. And if you look at the very top, it says that the numbers that are in light face are for alpha of 0.05, and the numbers that are in bold face are for an alpha of 0.01. and all of the alphas are for a two-tailed test. It doesn't say that, but that's what it is. And you can assume that unless otherwise specified, you'll always be testing at an alpha of 0.05. So now let's use this table for our sample. So we know that our degrees of freedom between equals 2 and our degrees of freedom within equals 15. But you may be looking at this table and saying, oh my goodness, it talks about the numerator and the denominator, not between and within, and I'm panicking and I just want to go hide under my bed and freak out. And I, of course, don't think that that's what you should do. Take a couple of deep, healthy, nice breaths. Tell yourself that it's going to be okay. I'm not going to leave you floundering. And what are we going to do? We are going to look at the formula because formulas are our friends. So if you look over here at the formula for f, you can see that mean square between is in the numerator and mean square within is in the denominator. So if you want to know the degrees of freedom for the numerator, that means you're going to be looking at the degrees of freedom between. And if you want to look at the degrees of freedom for the denominator, that means that you're going to be looking at degrees of freedom within. So let's go ahead and do that. So we know that our degrees of freedom for the numerator is 2, and our degrees of freedom for the denominator is 15. And if you put your fingers and trace those columns and rows together until they touch, you will touch at 3.68. So we know that our critical value for this data set is going to be 3.68. And if you remember from before, our calculated value of f is 24.64, which means that our calculated value of f is in that gray shaded region. So our f critical value is smaller than our f calculated value. 3.68 is smaller than 24.64, which means we can reject the null, and it means that we have supported our alternative hypothesis. Now, it was a long time ago, I feel like it's been a long time, since we talked about our null and alternative hypothesis, so let's refresh our memories. The null is that there's no difference, and the alternative is that there is some difference. And so we've done all of these analyses, and we can say that we can reject our null hypothesis and that we've supported our alternative hypothesis. So we can say there is a statistical difference in how many people purchased red, blue, and black cars. So here's all the numbers that we're going to need on the screen to write an APA-style report of our analysis. And this is what a sentence would look like. And you can see you're essentially stating that there is a difference in how many people purchase red, blue, and black cars, and you're reporting an APA-style report for an ANOVA. So you give the F value, then you give your degrees of freedom between and your degrees of freedom within. Then you report the actual calculated value of F. You say whether P is greater than or less than 0.05, and in our case, because our critical value of F is smaller than our calculated value of F, we know that P is smaller than 0.05, so it's significant. And we also give a measure of effect size, which is eta squared. And some of you may be saying, well, we want to know which kind of car is purchased more than another kind of car. And if you want to know that, then you're going to need to do a post hoc test, which we will not be covering in this video. And so if the managers of this dealership came to us and said, we want to know whether we should get more red, blue, or black cars, we, on the basis of this analysis, could not tell them that. All we could tell them is that we know that there are some cars, color of cars, that are purchased more than other color of cars, but we don't know what the difference is. And again, we won't be covering post hoc tests in this video. So all you can say at this point is that there is some difference. You can't say where the difference is. And that is how you calculate a one-way between subjects ANOVA.